So we can kind of use that idea to summarize as follows. So suppose that V is a vector with initial point P1. So we're going to label the X and Y values for the first point with that little 1 as a subscript, just so we can show the difference between the first point and the second point. So if the vector is created by going from the first point to the second point, then the vector V is equal to the position vector. And that position vector is going to come from taking those X values and subtracting them from each other. So X2 minus X1 and Y2 minus Y1. Another algebraic way of representing vectors is by using unit vectors. And so where unit vectors are, those are where you have a magnitude of 1. So a vector U for which the magnitude equals 1 is called a unit vector. And remember, this symbol stands for magnitude. All right, so if we continue learning about unit vectors, we're going to learn a couple more names for them and some more terminology. So I, this does not mean the imaginary I. This is going to be a vector I. So you can see that as a bold I. So if that's a unit vector, and it's a specific one whose direction is along the positive x-axis. So you can see I written right here. So I is a unit vector, so that means its magnitude is 1, so the length of it is 1 unit, and it's whose direction is along the positive x-axis. J is the unit vector whose direction is on the positive y-axis. Okay, so if we had to write these as components, I would be over 1 up 0, and then J would be over 0 up 1. So therefore, any vector can be written as the vector of A and B, or we can rewrite it as that, because again, if these are scalar, this would just get multiplied in and we'd get A plus B times the vector 0, 1. So again, if we multiplied this through, you're going to get 1 for that Y value. So then that ends up the way that we can write this. So if we're writing unit vectors, if you're taking a regular vector and writing it as a unit vector, you would write it as AI plus BJ. So for example, if we had to rewrite the example 2, which was 9, 2, and we wanted to write that using unit vectors, this would be 9I, so 9 units to the right, plus 2 J's. Okay, let's look at another example. So here we've got the graphs written, and we need to find the vector U and vector V in this unit vector format. So first, let's write U as a component vector. So for U, we're going over 2 and up 4. So it'd be written as 2, 4. Now, if I wanted to write it in this format, it's going to be 2 vector I plus 4 vector J. And then for V, that's going to be as a component. It's going to be over 2, down 2, so 2, negative 2. If I was writing it with these unit vectors, it'd be 2I minus 2J. So if I had to add these two together, so first, let me just show you, if you didn't have the visuals of this, that literally would just be adding these two components together. So that would be 2 plus 2, 4 minus 2, which gives us 4, 2. We can also double check that based on the picture. So this line right here is U plus V, and you can see it goes over 4 and up 2, which is exactly what we got for the component vector. Same thing when we go to subtract these. I'm going to use a different color. So this would be U minus V, which gives us, so the vector U is 2, 4. We're going to subtract 2, negative 2. So that would give us 2 minus 2 for the horizontal component, and then 4 minus a negative 2 for the vertical component, which gives us 0, 6. We can double check that. So if I go to graph this, you've got U going in this direction, and now V, instead of it going down, we're going to be going up. So that's a vector that's going to go to the left, so negative 2 up 2. So negative 2 up 2 is going to put me right here. And you can see when we add these two together, you're going to get right at 0, 6. Now, if we needed to find 2u minus 3v, so I can just use this algebra too, you can totally graph it, but we can go through and say this. So this is going to be 2 times u minus 3 times v. Okay, so that's going to end up giving us 4, 8, because 2 times 2 is 4, 2 times 4 is 8, minus 6, oops, plus, I'm going to do plus. Oh, no, we'll stick with minus. So minus 6 and negative 6. So that's going to be 4 minus 6. And 8 minus a negative 6, which gives us negative 2, 14. Now, if we had to find the magnitude, which is the length of u plus v, so we know the component vector for u plus v is this. So this again equals the length. So this is just going to be using that x squared plus y squared equals r squared. So the magnitude is going to end up equaling the square root of the x component. So our x component was 4 plus the square root of the y component. So that ends up giving us the square root of 20, which 20 I can rewrite as 4 times 5. So that's the square root of 4 times the square root of 5, which is 2 root 5. Okay, so when you're adding them, you can, and subtracting them, you literally can just add the horizontal components or subtract them and add or subtract the vertical components. When you're multiplying by a scalar, you just take those the vertical and horizontal components and multiply them by each scalar, then you add or subtract normally. And when you're finding the magnitude, it's the square, so you do the square root of, you take the x value squared or the horizontal distance squared plus the vertical distance squared, because again, this is just finding that hypotenuse. Okay, so let's talk a little bit more about unit vectors. So if we are, what we just saw in the other thing is if we're adding two vectors together, you basically add the horizontal components, and then you add those vertical components. If you wanted to write this in this format, it would just be a1 plus a2 I plus b1 plus b2 j. Similarly, if you're subtracting them, like we saw, we subtract the horizontal components together. And then if we're multiplying by a scalar, so if I took a scalar and multiplied it to vector v, all that does is you just move that number inside. So it's going to be 3 times a1 and 3 times b2. And then if you had to find the magnitude, so to find the magnitude, it's taking the square root of a1 squared plus b1 squared. So you take the horizontal component, square that, plus the vertical component, square that, and then you find the square root of that. So recall that a vector u for which the magnitude of u is 1 is called a unit vector. Just like a unit price at the grocery store can be found by taking the price of an item and dividing it by the number of units it contains. A unit vector, we can do something similar to find that. So it's found by taking the vector and dividing it by its magnitude. So unit vector in the direction of v theorem. For any non-zero vector v, the vector u, so the unit vector, you would take the vector to get it to the unit vector and you divide it by its magnitude. So it's a unit vector that has the same direction as v. So in other words, v is the same thing as the unit vector times the magnitude. So here's an example of this in action. Find a unit vector in the same direction as that vector. Okay, so the first thing that we want to do, so first of all, we know that the unit vector equals the vector divided by the magnitude of that vector. Okay, so we already know the vector is this. So let's find the magnitude of it now. So the magnitude is found by taking the square root of the horizontal component squared plus the vertical component squared. So when I do that, you end up getting the square root of 169, which is 13. So if I were to write this, I would get the unit vector is 12i minus 5j, so it's what the actual vector is, divided by magnitude. So in other words, we could rewrite this as 12 over 13i minus 5 over 13j. And in many applications, vectors are described in terms of magnitude and direction rather than in terms of its components. If given magnitude and direction, how can a vector be expressed? So for example, a ball is thrown with an initial speed of 90 miles per hour. This is known as the magnitude of the ball, so how fast it's going. When the ball is released, the angle it makes with the horizontal is 30 degrees. This is known as the direction of the ball. Okay, so to find the terminal point of the vector, use what you know about trigonometry to find the x-coordinate. All right, so we know the x-coordinate equals r times the cosine of theta. Okay, so my radius, my r is 90, cosine of 30 degrees. So I get 90 times root 3 over 2, which is 45 root 3. And then if we're looking for the y-coordinate, well, we know that y equals r times the sine of theta. So 90 times the sine of 30 degrees, which gives me 90 times 1/2, which is 45. So now we know what this actual point is. So the point is 45 root 3, comma 45. Since the vector is a position vector, initial from the origin, then its simplified form we can write as 90 times the cosine of 30 degrees I plus the sine of 30 degrees j, which equals 45 root 3I plus 45j. Of the initial speed, how much is in the horizontal direction? So horizontal direction is the 45 root 3. So when you plug that into a calculator, you're going to get about 77.94. And this is going to be in terms of miles per hour, since that's what the unit was. So we know horizontally it's going 77.94 miles per hour. And then if we had to figure out the vertical direction, that's the 45. So that's going to be 45 miles per hour. So this is really helpful when we're talking about airplanes, their ground speed versus their airspeed. It's going to really come into play.